Mm. Oh. So today we will study this brief introduction of partial differential equations and how to solve these partial differential equations. We will do it in the next class. Tomorrow I will not be able to take class because of our one of the college function which we will organize tomorrow among the teachers. It's a farewell program, and I'm the secretary, general secretary of our teachers organization, Pukta. So I will not be able to take class tomorrow, and Friday I will try to take class at we'll see which time is convenient. Probably around 1:30 I can take class again at Friday. And yeah, we have studied what is that Runge-Kutta method up till Runge-Kutta method, and the remaining technique for solving numerical technique for solving ordinary differential equation is predictor corrector method. So that predictor corrector method, I will do it. I will discuss it after this partial differential equation. So today we will just jump from uh, uh, ordinary differential equation to partial differential equation. Once we complete partial differential equation, then we will get back to that predictor corrector method of solving ordinary differential equation. So nowadays, like our undergraduate examination is still going on. As a part of examination cell, I am engaged with examination duties. So I could not take class during my proper time slot. So hopefully I will be able to take class again at 1:30 on Friday, as I said before. Now, in that Runge-Kutta method, I think before I conclude my lecture, I don't know whether I gave you like a kind of exercise. So I will give you one more exercise. Solve the differential equation. It's a simple thing. So you can see my PowerPoint, I guess. Oops. Why is this thing, what is wrong? I cannot write anything. What is wrong with my stylus pen? For some reason I cannot write anything. But it was working yesterday. If it doesn't work, then I have to buy a new stylus pen. What is wrong? Let me reshare my pen drive, my PowerPoint. My stylus pen was working till yesterday. What is wrong with this? Some reason it is not working today. If my pen is not working, I cannot write anything on my screen. Just a minute. What has gone wrong with my pen? The internal battery is gone or what? Then I have to go out to market and buy the new one. Until then, I cannot do anything. Oh, man, my pen really is not working now. There are some buttons to press. but still it's not working. Okay, this has never happened with me before, so maybe something has gone wrong with my pen. I don't know how to correct it now. Therefore I cannot write anything without my stylus pen. Yeah, I will use that cursor, but when you use a cursor, it's very difficult to write it just with a cursor. Cannot write it properly with the cursor. Anyway, I will have to use a cursor. Here you have what is called annotate. So I have to use this draw. No other choice. Okay, I will use this, even though I'm not so comfortable with it. Oops. No, again. I'm without pen again. I will use this draw. All right. So we will study partial differential equation. I think everybody knows the difference between ordinary differential equation and partial differential equation. So in ordinary differential equation, we are dealing with a certain function. Let's say a certain function, let's say u, which is a function of single variable. If certain quantity is a function of one independent variable, x, something like this, then you can perform differentiation of this function with respect to x only, du upon dx, and the equation involving the differentiation of that function with uh, uh, derivative of that function is called ordinary differential equation. Here it could be y minus x square or y minus x or whatever it is. This is what we know it as ordinary differential equation, ODE. Oh, this is so difficult. ODE, ordinary differential equation. Now, we often have in physical and many problems in engineering and physical problems, we often have a certain function which is a function of more than one variables. Like let's say if u is a function of x, one space coordinate and another time coordinate, or you can have a function of two space coordinates x and y, or a function of three space coordinates x, y, z, and three space coordinates plus one time coordinates. Then the equation involving such function which depends on more than one variable will have a differentiation. It can have differentiation with respect to x, and also with respect to t, and with respect to y, with respect to z, like that. So that kind of equation is called partial differential equation, because the differentiation of u will now be partial differentiation. So what is a partial differentiation and ordinary differentiation? Here you see that in ordinary differentiation, this u can change only with respect to x. So whatever changes, small changes in x, whatever small changes in x you have, that is the only influencing factor for this quantity u. So du by dx, as you know it, as I have written, explained it before, it will be del u upon del x. So it is a du by dx is a measure of the change of u with respect to a small incremental change in x, considering the fact that the change in x, del x, is very, very small. Del x tends to 0. Okay, so this involves what is this differentiation is called ordinary derivative, ordinary differentiation, for the fact that you can only change with respect to change in x. Now, if you have a function u of more than one variable, like for example, this is a certain function, not only that it changes along x-axis, it also changes with time. As time passes, the functional value also changes. So there can be more than two factors that there can be two factors here, the space x coordinate and the time t coordinates, to cause any change or alteration in the value of u. So in that case, you are no longer having normal derivative. You have to measure, you have to perform what is called partial derivative. Del u upon del x. You can have del u upon del x as well as del u upon del t here. Del u upon del t. So what it means is that del u upon del x is simply how quickly the function u changes with x changes, or del u upon del t is the rate of change of u with respect to time. All right. So not only that u can change with x, it can also change with t. Therefore, whatever derivative, whatever changes we measure, or whatever like measure we take to estimate how the dependence of u on such variables like x and t, it is now what is known as a partial derivative. So for partial derivative, instead of d, we use del here, del. So my handwriting is even poorer than what it normally used to be. So del is called your partial derivative, del operator, del. Okay. Now, yeah, how do I move to the next slide? Oh, in order to move to the next slide, I have to close this once again. Now I can move, I hope. Yeah. Array, this is still there. No, this is so difficult. In the morning, I went out to market. Had I known that my pen would not be working, then I would have purchased a new stylus pen. Now I'm compelled to go out again. Come on. How do I delete this? In every pages, whatever I'm writing here, it will go to the subsequent pages. Come on, stop sharing, and then yeah. Okay. So a partial differential equation is an equation which includes derivatives of an unknown function with respect to two or more independent variables. And here in many physical problems like wave propagation, fluid flow, and vibration, stress, strain, material heat flow and distribution, electric fields and potential, diffusion of chemicals, electromagnetism and quantum mechanics. In this kind of physical and engineering problems, we often come across partial differential equation, because we often come across a certain quantity which is depending on more than a single variable, right? So this partial differential equation can be used for weather prediction that includes heat transport and cooling, advection and dispersion of moisture, and all these things. Okay, so to predict weather, one need to solve what is called a very complicated coupled partial differential equation. Yeah, I think here is something. Yes. Instead of using a notation, I think I can use pen here. Is it? If I use pen, can I still move? Yes, now I find a solution. Okay, anyway, now I can use this pen. Initially, I was using a notation at the top, but at the bottom here, we have another pen option. So this can be used for prediction of weather. We will have to solve a very large systems of coupled partial differential equations for momentum, pressure, moisture, heat, etc. Right now, uh, we can have what is called a linear second order partial differential equation or non-linear. So whenever we consider linear means, so this is the general form of, before that, this is the general form of linear differential equation. Okay, this is the general form of linear differential equation. And in this general form of linear differential equation, as you can see, even though there is a second order derivative, del square del x square, second order derivative is there, del square term, second order partial derivative, but it does not involve nonlinear term. Nonlinear term means if you have a square, this is called nonlinear, or if you have del square u upon del x square, del square u upon del x square, and if this whole quantity is square. Okay, so there is a quadratic term on this second order partial derivative. So in such case, we call the differential equation as nonlinear. So in this class, in this topic, for solving this like numerical techniques, we will only deal with the simple linear partial derivatives. Okay, linear partial differential equation. So there can be like a very broad tree classification for partial differential equation. The broad tree classification is that the first one is that, like if you look at this, the coefficient of del square u upon del x del y is called b. The coefficient of del square u upon del x square is a. The coefficient of del square u upon del y square is c, and we have another term called d. So b square minus 4ac, if it is less than 0, we call this elliptic partial differential equation. And if this is equal to 0, we call this a parabolic partial differential equation, and so on. So we call this as a hyperbolic partial differential equation. And each classification or each category describes a different phenomenon, right? So we will see that. Now, elliptic partial differential equations. Elliptic partial differential equations only involves what is called steady state in time. That means the function is having no time dependency. Okay, the function is having no time dependency. So elliptic partial differential equations does not involve derivative with time. The derivative of the function with time is always 0 in this elliptic partial differential equation. And uh, here uh, usually we define, later on we will discuss, yeah, I think I should discuss this later on. So usually we define with certain boundary conditions, like the functional value u, at the boundaries, as well as the derivative, the first order derivative at the boundaries. Here eta simply means it can be x, y. So instead of writing del u upon del x and del u upon del y separately, we simply write del u upon del eta. Eta is either x or y. Now, the typical example of this partial differential equation is what we know it as a Laplace's equation. So we know that in Laplace's equation, three-dimensional Laplace's equation, this del square u is equal to 0. When del square u is equal to 0, this is called Laplace's equation. U is the electrostatic potential, and in three dimension, this is called del square u upon del x square plus del square u upon del y square plus del square u upon del z square equal to 0. So that means there is no time dependency of this function on t. there is no time dependency of this function u, right? So steady state system, partial differential equation, elliptic partial differential equations involve steady state systems like this, electrostatic potential in a particular space. So here, if you look at this Laplace's equation, del square u upon del x square plus del square u upon del y square, you see that the coefficient of del square u upon del x square is 1. And the coefficient of del square u upon del y square, if you compare with this, del square u upon del y square coefficient is c. So c value is 1. And the coefficient of del square u upon del x del y, that is b value is 0, because there is no term, what is that, there is no del square u upon del x and del square u upon del x del y. So we don't have this term, del square u upon del x del y term. So therefore your b value is 0, right? Your b value is 0. Now if you estimate b square minus 4ac, b is 0, minus 4 into 1 into 1, this would be minus 4. So in this elliptic partial differential equation that involve steady state system, no time dependency of u, then b square minus 4ac is less than 0. If it is less than 0, then that differential equation is classified as elliptic partial differential equations. And similarly, Poisson's equations, you know that Poisson's equations is when del square, if u is the electrostatic potential, del square u is equal to rho. Rho is charge density. Rho is charge density, which is depending on space coordinates like x, y, z. And we don't deal with non-static charge distribution. Non-static charge distribution means rho also has dependency on time, right? So in addition to x, y, z. So only if we consider static charge distribution like rho as a function of x, y, z, then that is your elliptic equations, because you will just calculate, you will just find the coefficient of del square u upon del x square, del square u upon del y square, and del square u upon del x del y. So that is b, and b square minus 4ac less than 0 is satisfied, means the Poisson's equation is also elliptic partial differential equations. So the boundary conditions, possible boundary conditions for elliptic partial differential equations are, the first one boundary condition is called Dirichlet boundary conditions. In this Dirichlet boundary condition, the functional value, u value, the value of the function u is provided along all the boundaries, along all the edges of the boundaries. Then we have what is called Newman boundary conditions. In Newman boundary conditions, del u upon del eta. Here eta can be x, y, and z. That means del u upon del x, del u upon del y, and del u upon del z in three-dimensional system. This first derivative with the space coordinates are given, the values are given along all the edges, along all the sides, along all the surface. Then this boundary condition is called Newman. And the mixed boundary condition is when u value, the functional value is provided for some of the edges, and del u upon del eta is provided for the remaining edges. So these are called mixed boundary conditions. So it is something like this. So let us see like an example of a two-dimensional system. Here u is a function of x and y, u is a function of x and y, and if we have charge density within this space as 0 and the electrostatic potential within this space, the electrostatic potential within this space is due to certain charge distribution outside this space. And in Dirichlet boundary conditions, here let's say this is your origin, this is what this exists, x means here this is your x value is here, x value is 1, okay, x value is 0 here, x value is 0 here. Or along this line you will find that y value is so difficult to write. Y value is 0, and along this line you will find that here y is 1, y is 1. So if the functional value u is given at x y equal to 0 along this edge, and the functional value u is given at x equal to 1, this edge along this line, along this edge, x value is always 1, right? And y value goes from 0 to 1. And if it is also given along this edge, y value is always fixed, y value is always 1, x value goes from 0 to 1. And along this edge, x value is 0 always. Along this edge, x value is always 0, y value goes from 0 to 1. So along all these edges of our problem, if the functional value is given, that boundary condition is called the Dirichlet boundary condition. And similarly, if del y upon del u upon del eta or del u upon del y along this line, the function which changes is your y only, del u upon del x, del u upon the del u upon del y, del u upon del x, del u upon del y. So if all these derivatives values are given along the edges, then that is called Newman boundary condition. And if the known quantities are mixed, some values of u are known for some h, and some values of del u upon del eta are known for the remaining edges, then that is called your mixed boundary condition. Now so today is just an introduction because I cannot do anything without my pen. It's so difficult to write. This parabolic boundary equations. So the parabolic partial differential equations are when b square minus 4ac equal to 0. And in these parabolic equations, we can have a first derivative in time. We can have a first derivative in time. That means non-steady system. Parabolic equations deals with non-steady system. So you can have variation in space coordinates as well as time coordinates. Your function, a certain quantity you measure, a certain function you measure, it could be temperature, it could be heat transfer or anything that has a space dependence as well as time dependence. So the initial value, typically like in parabolic equations, the initial values are given, the initial values of the function are given at t equal to 0. And also those we can have a boundary conditions. We have kind of boundary conditions: x equal to x naught boundary, y equal to y naught boundary, x equal to xf, x equal to yf boundary for all t. Okay, so all changes are propagated forward in time, that is nothing goes backward in time. So this is one example of parabolic equations. If you look at this one-dimensional diffusion equation, advection diffusion equation, here the coefficient of del square u upon del x square, that is what you have here as a here. In the general, del square u upon del x square is a, del square u upon del x del y is b, del square u upon del y square is c, right? So this k is now what is known as ka. Here you don't have del square u upon del x del y, so the mixed partial derivative you don't have, so b value is 0. And also you don't have del square u upon del y square, so c value is also 0. That means b square minus 4ac is 0. B square minus 4ac is 0. Therefore, this one-dimensional advection diffusion equation is called is one of the parabolic partial differential equation. Okay. Now we will explain how it is this can be solved using numerical techniques. But before that, let us just quickly go through this definition only. So here upwards is the time axis. Upwards, as you see, is the time axis, and horizontal is the space coordinate x-axis. So this baseline is when t is 0. Baseline is when t is 0. That means if the functional value is given at t equal to 0, the functional value given at t equal to 0 is called initial value. Okay, initial value of the function u. Initial value of the function u. Okay. Then here along this line x value is 0. Along this line x value is 0. Along this line x value is 1. Along this line x value is 0. So t exists, time propagates along this line. Okay. Now hyperbolic equations are when b square minus 4ac is greater than 0. It involves second derivative in time. So hyperbolic equations examples are our Schrodinger equations and all. It involves second derivative in time. In Schrodinger equation also you have a second derivative in time. In parabolic equations you have first derivative in time. In elliptical equation you don't have any derivative in time. The function is independent of time. Steady state system in elliptical partial differential equation. So here in this hyperbolic equations, you can have both variation with respect to space as well as time. Variation with respect to space as well as time. So the initial values are the function initial values u, x, y at t equal to 0. The first order derivative with respect to time at t equal to 0 is called the initial velocity. And you can have another boundary conditions like this is the initial value of x, the initial value of y. So for all t, you can have these boundary conditions and similar to that. Okay. Now, yeah, this is one of the wave equation, simple classical wave equation. In this simple classical wave equation, also del square u upon del x square coefficient is 1. So that means a equal to 1. And there is no mixed derivative of u and y. There is no term such as del square u upon del x del y. So b is 0. And c, as you see here, del square u upon del t square, c is 1 upon minus 1 upon c square. Now if you calculate this b square minus 4ac, b square is 0 minus 4 into a is 1, c is 1 upon c square. So if you look at this quantity b square minus 4ac is greater than 0. So because here you have what is called c as minus of 1 upon c square. So 4 upon c square is greater than 0. So this kind of wave equation is called hyperbolic equation. Wave equation is called hyperbolic equation. And using these hyperbolic equations, we can model vibration of a string, water waves, voltage changes in the wire. And in this case also, you can have initial conditions like the initial condition of the function at t equal to 0 and the initial condition of the time derivative at t equal to 0. And yeah, along this line, your x value is 0. Here x is 0. If you look at this system, x exists, this exists, your x exists. So here at this point x is 0, at this point x is 1. So it will propagate with time. So these are the boundary conditions. Okay, so how we are going to solve this kind of differential equation? We are going to use what is called finite difference approaches and finite element methods. And this I will have to discuss it in the next class because I don't have pen with me. So yeah, I have to discuss all these things. I will stop now because I cannot write anything without writing anything. I don't think I should continue further. I need to buy my stylus pen. It's quite difficult to use my touchpad. I don't have a mouse and I use my touchpad. It's quite difficult. let us stop now for now. Okay. Thank you everyone. So let me remind you, tomorrow I'm not going to take class because I have to involve in organizing farewell function of one of our senior teacher. Day after tomorrow, if possible, I will try to take class at 1:30 again. Okay. Bye everyone.